So what I did was I showed that if you have a partially ordered set, then you can embed it within its, this is the poset of all down sets. In fact, this is not only a poset, we showed that this is actually a complete lattice. That means all subsets of a partially ordered set in which every subset has a supremum and every subset, and therefore every subset has an infimum. So you can embed it over there, and the way you do it was by taking P to the principal downset. Well, this is still something else, so let's give another color. And then if you had any other partially ordered, let's say any other partially ordered set, with uh, with suprema for each subset. Such things we will call them sublattices. So it doesn't have, so it has suprema for each. Actually, if you take, if you have suprema for every subset, then you have infima for every subset also. This is a very happy consequence in the case of posets. But here we would not have, for this one, we would not concentrate on the existence of the infima, but we would look into the suprema only. And this is any order preserving function which preserve the suprema. Now this obviously means whichever suprema exists in P, so that means if you have a T in P and the suprema of T is a member of P, then this implies that f of this is equal to the suprema of in A. Okay, so if that is the case, then there exists a unique where f star is a suprema preserving function, and f star over downset, sorry, over downset, this became the suprema over this. And the reason behind this was this expansion which we computed. Okay. And therefore, it turns out that f star composed this becomes f. So it was this extension property. That was what we completed last time. And then we said that you could phrase this also for, so suppose if you have, if you take P op, that means P with the opposite order, then you should also have a similar situation over here, downset of P op, and it says therefore that whatever f you have over here with f preserving suprema over here, then there exists this f. Now let's unfold this. So suppose if we have a downset of P op, so what does it mean? So this means that if we have x, so firstly S is a subset of P, and if this is the case, remember this is the opposite order, so let me write it in this way. Then it means that x is an S. Now if you unfold this, this becomes that y is less than or equal to x and y is in S implies x is in S. So this is typically kind of saying the dual of an up and down set, so we often call it an upset. And the set of all such things is obviously denoted by upsets of P. So now, therefore, it turns out that we were made, the lattice over here was comparing the upsets by subset relation. So over here, upsets would be compared by inclusion relation. So this is nothing else but upsets of P with the opposite order. Okay. So with the opposite order, that's what comes over here. And then in place of sorry, not here exactly. So this is my upsets of P, and over here, what is this map? What is this map? So let's write like this in the opposite. This is the set of all x in P such that x is in this opposite order of P. So this means x in P says that P is less than or equal to x. So this is exactly can be written like this. This is the smallest upset containing, right? So this will become this. Now, this doesn't become, so this takes the suprema in upsets, in the opposite. So suprema in, so suppose now let's see. So if you take a subset, T of S, then the suprema in the opposite poset of T is obviously the infima of T. So, and this is the, so if you write this now completely in terms of P, this is going to turn up to be and this map now preserves all meets or infinite. And this one is the extension which preserves meets them enough. So if we, so this is just the unfolding of this original, this picture. So now let's put all of this in the same diagram. Let's see something comes up now. So given any partially ordered set, we have downsets of P and we have upsets of P. And this is mine. Remember, both of them are complete lattices. Let me write them in another color to show that they are actually this. So both of them are complete lattices. So therefore, in particular, this one has all suprema. Now this map is obviously preserving all the suprema. So therefore, from its property, there exists a unique map. And what does it do? So so I'm saying it like this. Let me not write it like this. So let me say, so what does it do? It, if I take a subset, say T of P, so this one, let me, how do I, so I take a subset of P of, so this map is actually taking P to downsets of P. This one is taking a subset P to upsets of P. And this is taking a subset T to the set of upper bounds of P. So I leave it to you to check. So this unique map, which comes from this, so this formula will give you the set of upper bounds of P. Okay. Obviously, the upper bound of P is any set. If you have an upper bound, anything bigger than that is also an upper bound. So it's an upper. So this, shall we write it like this? A blank and then and U on the top. And by the same token, since this has, so I have this unique map which takes a subset S over here to the set of lower bounds of S. Okay. So you have this beautiful diagram. One takes upsets to the set of lower bounds of that, and another takes. So let's try and figure out. Suppose if we have a partially ordered set like this, okay, and if we take this to be our, let us put another thing over here. Say, let's say this. So this is all saying these are the bigger ones. Okay. So that's what I'm trying to indicate by this partially ordered set. If we take this subset, if this is our subset, then the set of upper bounds of this, well, the set of upper bounds of this will be given by this set, because this element is bigger than this, right? But we don't know about this. So, and if we take this element, this is bigger than this, but it is not bigger than this. So you see over here, in this particular case, the set of upper bounds of T is empty. What are the lower bounds? Something which is smaller than both of them. So we see this element is smaller than this. And here, this element, that's not smaller than any of this element. We cannot say anything about this element and any one of this. So there is no element, so it can as well be like this. Okay. So this is the empty set. Whereas if you take the, now what is the set of upper bounds of the empty set? So what does this mean? Okay, so let's rewrite this. X is in Tu if and only if the moment you take a T from T, you must have X to be larger than that. So this therefore tells us that if T is the empty set, this is always this is always false. So this statement is trivially true. So the set of all upper bounds of the empty set, if you take anything, this is the whole set. Okay. And similarly, uh, that means the whole poset, the whole set. Okay, we write it like this. So this is similarly this. Okay. Now, so let's come back. So what is happening? If we take anything over here, we can, the situation is we can embed this P inside a complete lattice in a way in which all the, in a beautiful way in which the joints are preserved, and in another way in which the meats are preserved. Now, about these two maps, there is something nice. Suppose if we have, so let's observe further. S is a subset of, let's see. So T is a subset of, so what does this mean? Well, this means that T belongs to T implies T is in itself. So this means that, which is the same thing as saying that whenever you take a T from T, and whenever you take any S from S, this means that T is less than or equal to S, right? So it is telling, therefore, that this is the same thing as saying that and this therefore is the same thing as saying, so I leave to you again a little bit same story. So it is saying that S, that the upper bounds of U is contained in this. So it turns out that T and S always have this connection. So what happens? There is a very nice connection between these downsets and upsets. This is often called a Galway connection. So to be more accurate, so here is a definition. If X and Y are posets, are order preserving maps, then we say there are many things we say. We either say that this the pair if G constitute a Galway connection, Alternatively, we say that F is left adjoint to G. Alternatively, we say G is right adjoint to F. So all these things are synonymous if this condition holds. If X is less than or equal to Y, if and only if X is less than or equal to Y. So examples. So we actually this is a glaring example. There are several other examples which we use as we go, but here are some facts which are evident from this. Firstly, we will see that this is always true. The maps are potent and extensional. I'll say what does it mean. And 3, GFG is equal to G and F is equal to F. Now what are these two? Well, let me put this here. So suppose you have any P is any order result. So it is called H is extensional if for every X. So that means if you think of X, so Hx is trying to cover to 1 minute. I made a mistake over here. H is trying to cover the extent of H, so something like that. Its dual is intensional. Possibly this is the if Hx is less than or equal to X. And it is what idempotent? Idempotent means if H composed, H is H. So I should, the mistake over here was 1 minute. And GF is extensional if G is intension. And finally, as I said, GFG is equal to G and FGF is equal to F. So these are very simple consequences of this check. So this is can be looked upon as. And there is one more, a little something what comes up a little more. So suppose if I have T to be a subset of X and supremum of T exists in X, then f of the supremum of T is join of this. And dually, if you have a subset of Y and the infimum exists in Y, then f of the infimum is actually the infimum. So the left adjoint preserves all supremum and the right adjoint preserves all infimum. A nice way to write this is, okay, we write it like this. Say that F is the left adjoint. Okay? So, and finally, if X and Y are complete lattices, F preserves supremum or respectively. G preserves infimum. Then one, then there exists a G, so respectively there exists a F such that F is left adjoint. So it is kind of converse. So it says, suppose if you have, in the case when X and Y are complete lattices, and you have a suprema preserving function from X to Y, then you have a function G, which is the right adjoint of F. And dually, if you have a function G which preserves all infima, then you can find or describe the function F, which is the left adjoint of G. So you see, any one of them kind of determines the other in case of complete lattices. And well, I leave these 5 things as exercise. But now let's come and see what happens over here. So we have this Galway connection, right? So we have taking upper bounds is a Galway connection to taking lower bounds. All right. Now, suppose if we have a Galway connection in general, let's see something nice. What happened? Okay. Suppose if we have, assume we have a Galway connection over here. And remember, GF was an endomorphism here, which is extensional and, well, monotonic extensional and idempotent. So if you apply GF twice, GF of GF is same as GF. Similarly, you have another endomap over here, FG. So the moment we have an endomap, we can look into its fixed points. So we look into the fixed points of G. So what are they? They are obviously the collection of X such that GF of X is equal to X. And similarly, we have the fix of FG. What is this? This is the set of all Y in Y such that Fg of Y is equal to Y. Okay? Obviously, since these are subsets, we can expect that, let me write this properly. This is fix of. Now, suppose if you take an X from fix of GF, then your f of X, but that is same as f of GF of X. But you know FGF is actually equal to Fx, right? So therefore, this is equal to Fx, and if you take the Fg of Fx, this you know is same as F. Yeah. So therefore, why did I write this twice? So this therefore tells me that Fx is a member of, so I can write, in fact, I can write this as f of, Fg of Fx. So this tells me taking f over here lands me into this. And similarly, taking g over here lands me into this. So obviously these functions restrict to order preserving maps, which we write as F0 and G0, right? Obviously, the same relationship that was holding over here holds over here. But what also happens is further. Further, what happens is G0, F0 becomes the identity of fix of GF, and F0, G0 becomes the identity of fix of FG. So that means, so check this. So that means this adjunction, therefore, restricts to a subset of X and to a subset of Y, which as partially ordered sets are isomorphic. Okay? So the moral is every adjunction or every Galway connection restricts to an isomorphism of two posets. Okay. So if we come back here, now let's come back to this case. Where was I? Yeah, let's come back to this one. So I will have, so let's, so I have my downsets and my upsets of. So here you take the upper bounds, here you take the lower bounds. This is left adjoint, and this information we don't immediately need, but okay, we'll come back. So this is taking to downsets, this is taking to upsets. So all this information therefore tells us that, so what is fix of? So now let's see. Here, this one is composed. So you first take the set of lower bounds and then you take the set of upper bounds. So should we write this as, so what do? You take a set, first you take its set of lower bounds and then you take its set of upper bounds. So should we write this? So let's write this as LU. And similarly over here, this is UL. Okay. So here you first take its upper bounds and then you take its lower bounds. Okay. Obviously, your Galway connection is telling you that T is bigger than this. Obviously, it is telling you this is obviously this. Yeah. So you see, these is coming exactly from this. And then let me write this here on this side. Let me put it here. Yeah. So so now what is this? What is fix of? So what is fix of? So this is precisely those downsets which are for which if you take its upper bounds, so all the downsets for which if you take its upper bounds and then its lower bounds, they are exactly the same. Okay. And then you actually have over here, this is the set of all upper bounds, upsets, says that S is equal to SL. Okay. And we know that this is a subset of this is a subset of this, and this restricts to an isomorphism. So this is same as this. Okay. These two are actually same. Okay. So what we do is this common thing is often called, well, we actually write it in another way. So we often write this as, so let me introduce this. This is in fact taken like this. This is what is this? This is an downset and this is an upset, such that the upper bounds of L is U and the lower bounds of L is U is L. These members are often called the Dedekind cuts. It is exactly the same construction which was done by Dedekind for rational numbers. If you think what he was doing was, he was taking subsets of rational numbers which were downsets, pairs of subsets which were downsets and which were upsets. Okay, and well, what is the relationship? What is the ordered relation? So this is less than or equal to another such. So what does this mean? So if the lower, this is often, if this happens, or if the upper set shrinks or the lower set increases, and you define this, and it turns out that the join of this exists, and this is nothing else. What you take, these are downsets, so you take the joins of this and you take the leads of this, the infimum of this, and that becomes your essential, the required. So that's the Dedekind-MacLean completion of, and that is exactly isomorphic with this. And this P is actually embedded inside this. How do you take it? You take your P. Well, you take the downset and then you take the upsets of, so the upper bounds of this downset and the lower bounds of it. Okay. So that gives you, and that's, so that's, if, well, sorry, I need to give you and then, yeah. So that kind of gives you the analog of the rational numbers. And so this therefore becomes the this is usually called the Dedekind-MacLean completion of P. So that's so with that, uh, I have one more thing to say. So therefore, the upshot of this development is that you can embed, so every poset can be embedded inside a complete lattice, and in such a way that whenever you have any other map which preserves a suprema or infima, then you can extend that completion. So that's the, so in some sense the Dedekind-MacLean completion becomes best complete lattice counterpart of any poset. That actually brings me to the first end of the first part of this, what I wanted to say. In the next part, I shall further specialize to a very, so this is, the second part will be about, I'll take very special kind of, we shall consider very special kind of complete lattices. These are called frames. We looked upon, well, these are complete lattices in which finite meets distribute over arbitrary joints. We made a very small remark last time when I introduced a lattice. I showed that a lattice is nothing else but a set with two commutative monoid operations and having a handshake in the name of absorption property. With respect to handshake, I gave well, three facts. First is roughly what I gave you, the Hilton principle, which roughly says if two binary operations with identity elements shake hand too much, they will become identical. In the sense that if each is a homomorphism of the other, then they become identical and they become nothing else but a commutative monoid. There was another kind of handshaking that I showed was the distributivity. For instance, for multiplication over addition in the case of rings. And we will see that not all lattices have this distributive property. And this distributivity is actually not the Ekman-Hilton type handshake, which is much more restricted. So we will see next time that if joins distribute over meets, then meets distribute over joins, and so on. And we will see that distributive lattices turn out to be much more well behaved than they are the non-distributive ones. And then we will see some kind of, we will come to this infinite distributive lattice. And then regarding examples of frames, to discuss this, we will finally show that these are some kind of generalization of the notion of a space. I hope you have seen what a topological space is, if not, yes. So This is some kind of a generalization of topological spaces, and that's exactly the arena of place of research, which is called point-free topology. And I'll finish with some pointers to references, initial references on this. So that will be my second part, and with that I'll stop here.